Good afternoon, everyone. Today, the Adamus seminar has the great pleasure of welcoming Dr. Dinis Abranches. Dr. Abranches completed his master and PhD in chemical engineer at the University of Notre Dame, USA, where he graduated with academic honors. He is currently an assistant research at the University of Aveiro, Portugal, working with the Virtual Materials and Artificial Intelligence Group. Dr. Abranches' research focuses on the fields of thermodynamics, artificial intelligence, and computational chemistry. He has a special interest in green solvents, including dipotactic solvents, hydrotopes, and ionic liquids. So, once again, welcome, Dr. Abranches. Thank you so much for accepting our invitation. It's a pleasure to have you here with us. Please feel free to start your presentation.
From noise to knowledge, stochastic machine learning for materials design. I'll start just with a brief introduction about myself. It's pretty much what Luan just told you. I did my undergraduate in Portugal in the University of Aveiro with Professor João Coutinho. I finished in 2020 and then I moved to Notre Dame in the United States where I did my PhD with Professor Ed McGinn and Professor Jamil Kalana. From there, in 2024, I moved back here to Aveiro, where I'm an assistant researcher. Most of the work that you're going to see today is from the time when I was an undergrad, then when I was a PhD, and then as an assistant researcher, I mixed all of it to create the story that I'm going to tell you today. So now I'm at the University of Aveiro, specifically inserted in SISECO, which is an associated laboratory. You can think of it as a research institute. SISECO is a very big research institute. It's not a research group, but it is composed of several different research groups. We have more than 200 PhD students. It's truly a multicultural and diverse multidisciplinary institute. Over 30% of our PhD students are international students. And I really like being here because of all of the multidisciplinarity. We're composed of chemists, chemical engineers, materials and ceramic engineers, physicists, physical engineers, product designers. So anytime we need a niche equipment, something that we have no expertise on, but we would be interested for our work, we only really need to go into the hallway, go down the hallway, and we'll find someone that can do the thing that we want to do. So it's really a unique experience to work in this type of multidisciplinary environment. Of course, the door is always open here at SACO, and I extend an invitation to all of you. Come visit us, see what we do, talk to us. We're always happy to share and collaborate. Now, about the research that I do, I focus mostly on the design of sustainable materials. And to that end, I employ thermodynamics, modeling, and since a few years ago, artificial intelligence as well. I'm quite interested in hydrotropy. You'll see a lot about this in this presentation and also in dipotactic solvents. The idea behind hydrotropy is the ability of enhancing the solubility of hydrophobic solutes in water. And we like it very much because, as you are aware, water is the greenest solvent. So we should be using it anytime that we can use water to process the stuff we want to process. Dipotactic solvents also quite interesting because it allows you to create liquid solvents from solid compounds. So all of a sudden, the range of things that you can use as a solvent basically explodes, becomes virtually infinite. All of this, of course, needs some understanding and modeling techniques so we can predict, anticipate, and characterize our materials. Now, about machine learning. Machine learning, you can think of it really as a black box. And this black box might be a neural network, might be a Gaussian process, can be a random forest, but for the sake of this presentation, let's think about machine learning as a black box. Usually, you want to give something to this black box, say a molecule, and you want this black box to give you something in return, a property. So for instance, if I input ethylene glycol into my model, I want my model to tell me 15.5 centiquats, the viscosity of ethylene glycol. And this works very well. I know sometimes it looks like magic, sometimes it sounds like magic, sometimes it is magic, but it works. But you need a lot of data. You really need thousands of data points for these models to work. And usually when you train your model with lots of data, you get a parity plot that looks like this. So the y-axis is a predicted property, the x-axis is a true property, and all of your data sits on top of the diagonal, which means the model is performing very well. But more often than not, you actually get this, which means that your model, for some reason, is not working very well. And when that happens, what most of us decide to do is, well, let's put more data into the model. And sometimes that doesn't work. And so we dig up those old textbooks, go to the library, find data sets, try to get data from somewhere from the past century or even from the 19th century. And we get to thousands, tens of thousands, even hundreds of thousands of data points. That's a lot of data. And sometimes that doesn't work either. And we start making up fake data using data augmentation techniques and whatnot, until eventually we've tortured the model for long enough that it will confess to anything that we want it to confess. And you can imagine that we might be able to do this when we have hundreds of thousands of data points, but for most of the applications that we care about, particularly to design new materials, particularly in niche fields within chemistry and chemical engineering, we don't have that much data. Sometimes we have 10 data points. Sometimes we don't even have data and don't know where to start. Does that mean that we are hopeless? No, we are not. Gaussian processes. This is what I mean by stochastic machine learning. They're a class of models that are non-parametric. That means that they have no parameters that need to be fitted against experimental data. Instead, they consider training data, F1 through Fn, so individual training data points, to be distributed in a multivariate Gaussian distribution. Now, when you assume this is, and this is a big assumption, but bear with me, when you assume this, you can then calculate probability distributions for new data that has never been seen before by the model using Bayes' theorem. And basically, you compute the probability distribution of whatever point you need. And that has an associated average and an associated standard deviation. So basically, you start treating data like random variables instead of actual scalar values. And what that means is, imagine that you have a function here represented in blue that you want to describe. You can actually train a GP model with a single data point. Of course, the prediction of the model is perfect on top of that point, but far away from that point, it sucks. However, the model is also telling you its own uncertainty about its predictions, this standard deviation here, which means that you can look at that standard deviation, find where it's maximum, and go to the lab and measure that point. And all of a sudden, you have a tool that can serve as your laboratory companion, telling you exactly what to measure to minimize the amount of data that you need to describe whatever properties or functions you care about. So let's start with an example. Diputetic solvents. We were interested in characterizing the viscosity of ternary DESs. Now, these were based on choline chloride and ethylene glycol, which does form a liquid, but it's a very viscous liquid. And we would like to modulate the properties of this liquid by adding a third component, water, acetonitrile, or DMSO. Now, our colleagues, our experimental colleagues, went to the lab and found that they needed to measure about 30 points to fully describe these viscosity surfaces. What you have here is the viscosity of this ternary mixture as a function of its composition and temperature. So a lot of data and noisy data. What if we use a GP? We start with a single data point, the viscosity at room temperature for the binary mixture. We train the model on this single data point, and then we ask the model, where should we measure next? Where is your uncertainty, or also known as acquisition function, where is it the largest? And the model told us to go to the lab and measure that point, because it's the furthest away. We went to the lab, we measured that point, and we retrained the model with now 2 data points. And we did the same thing. Okay, now where should we measure next? And the model told us there. And we measured there. 3 data points, refitted the model, and did the same thing. And then the model told us to measure that point. And by the 4th iteration, we had measured 4 additional points. And the model told us, well, my average uncertainty is below 0.5%, so you can stop. And all of a sudden, we didn't need to measure 30 data points selected on a grid that we just came up with. No, we allowed the model to guide us, and with just 5 data points, the binary one and plus the 4 additional ones that we measured, we can fully describe these complex viscosity surfaces. Now, we were also interested in trying this out for activity coefficients because it's not easy to pick models who describe the activity coefficients of mixtures. We have an RTL, Uniquac, things like that can correlate data, but they're not very easy to fit. Now, with Gaussian processes, because they are non-parametric, we don't have that issue. There's no functional form to be chosen. There's no how many parameters do we need to fit temperature in an RTL? No one knows. You can pick 1, you can pick 2. There's no such thing in GPs. You take a GP out of the box and you can start describing activity coefficients right away. And we tried this for a bunch of binary organic mixtures on large temperature ranges from 250 to 550 Kelvin, on full composition ranges from 0 to 1 mole fractions. And we found, to our surprise, that yes, we can describe these activity coefficients by fitting a GP model with the same level of confidence that we do when fitting in an RTL model. And as it turns out, this is thermodynamic consistent. It's not built into the model. The model is basically a stochastic model, but it's still thermodynamic consistent. And that means that if we have a GP model capable of predicting activity coefficients, we can then predict VLEs. And here you have the VLE of acetone water, the VLE of acetone methanol, the VLE of acetone hexane. And now, of course, this was fitted against an equidistant grid covering the full temperature range and composition range. But we were also able to predict LLE and SLE at temperatures far below the temperature range that we use for our training data. So the model can also extrapolate very well. Now, we had, of course, to pre-select 20 or 30 data points, like I showed you, to train the model. But we just saw that GPs can start with just a single data point and actually tell us what data they need to give us whatever predictions we need. So for a VLE, let's say we're interested in determining the VLE for a given mixture, we can start by assuming that the mixture is ideal, train a GP model on ideal activity coefficients. So basically at pure component mole fractions, activity coefficients are 1 across the temperature range, compute the VLE curve, which we show here in red, and then ask the model, what point should I measure experimentally to make this converge into the actual VLE? And we start as 1, 2, 3, 4 points, and we get the full VLE. Actually, for acetone methanol, a single data point handpicked by the GP was enough for us to describe its VLE. Acetone chloroform, 2 data points. Acetone tetrachloromethane, 1 data point. Acetone hexane, 4 data points. And these are not simple VLEs. These are not ideal mixtures. We have azeotropes here. We have severe deviations from ideality. And even in these scenarios, we take our machine learning model out of the box, never trained before. We train it on ideal activity coefficient. We ask it, what point should we measure? You measure that point and you get the full VLE. This is a huge increase in efficiency. You no longer need to go to the lab and measure 10, 15, 20 data points on some pre-selected composition grid. No, take a GP, let the GP guide you, and you'll find out that with a single, maybe 2 data points, you get your full phase diagram. Ternary mixtures, same thing. Here we have acetone benzene cyclohexane, acetone methanol benzene. 3 data points, again handpicked by the GP, were enough to fully describe these VLEs. SLEs for deputatic solvents, same thing. Here we have the solid liquid phase diagram of choline chloride urea. The model told us to measure this point and then that point, and there you have it. The GP fully predicts the remaining diagram. And what's interesting here is we actually tried to fit NRTL to just these 2 points that the GP asked, and we couldn't. Because, well, NRTL is a parametric model. It has 5, 7, 9 parameters depending on specific functional form that you choose. So you can't really fit it against just 2 points. GPs have no such constraints. Same thing for thymol menthol, same thing for thymol topo, just as a few examples. You can see more here in this publication. Now, if sometimes you've already measured your data and you just need some sort of model to pass through the data so that you can then do operations on that data, like calculating derivatives. You can use GPs for that too. For instance, here, we were interested in measuring the solubility of a hydrophobic solute in mixtures of hydrotropes. So basically pure water, adding a hydrotrope and seeing the solubility increase of a hydrophobic solute, syringic acid. And we measured this data as a function of composition and as a function of temperature. And to find out why we were able to increase the solubility of a hydrophobic solute by such a large amount, we wanted to do thermodynamic modeling. We wanted to take derivatives as a function of temperature, derivatives as a function of composition. But this is noisy data. Well, because GPs are stochastic, they can interpolate through this data without any issues. We don't need to choose a functional form for the temperature dependency. We don't need to choose a functional form for the composition dependency. No, take the model, fit against the data, model fits nicely. The model is differentiable, which means you can take derivatives and calculate things like solvation enthalpies, solvation entropies, and all of these thermodynamic constants that we thermodynamicists enjoy studying. Now, insofar, I've shown you GP models being trained where the input was always composition and temperature for a specific system, and the output was some sort of property. And this is quite useful when you've already defined the systems that you care about. So I want to get the VLE of acetone methanol. Okay, take a GP. Input is composition and temperature for that system. Output is activity coefficients or the VLE itself, depending on what you care about the most. But we can take this a step further. What if instead of inputting compositions and temperatures into our model, we actually input molecules? If we do that, all of a sudden, we can bring all of this stochastic nature and power of GPs into a space that is navigable. So a GP that would tell us, hey, if you want to extract this particular solute, you should pick that solvent and go into the lab and measure it. But this comes with a problem. And just to contextualize a bit why I think we really need to take these machine learning tools seriously, Here's an estimate by Raymond of how many molecules are out there. And if I were to ask you this question, and of course this is via Zoom, but if you want, you can still answer. How many molecules would you think, before seeing this slide, would you think are out there for us to synthesize, for us to prepare, for us to use as solvents, for us to use as materials? It turns out it's a lot. Raymond estimates that molecules up to 17 atoms, so small molecules, nothing fancy, no polymers, no peptides, no, small molecules, with just carbon, nitrogen, oxygen, sulfur, or halogen, so nothing with metals, again, nothing fancy. Just in this very small subset of chemistry, there are 160 billion molecules that are synthesizable and stable. 160 billion. To put that number into perspective, imagine that we all come together as a nice scientific family, and all of us start working on characterizing each one of those molecules. And we are very efficient. And under this scientific utopia, we can actually characterize a single molecule per second. It would still take us 300,000 years to fully characterize this space. And we need those properties if we are to decide whether those molecules are interesting for a given application, are viable to be used as materials. Do you think we can actually explore this space with experiments? With thermodynamic models? With molecular dynamics, Monte Carlo simulations, DFT, quantum chemistry simulations? No, it is simply not feasible. If we want to actually unveil this space and start generating molecules that we've never seen before, starting to get new things to use as materials, we have to use something different. We have to use something new. We have to use machine learning. And this is even a bigger concern when you go to mixtures, because when you go to mixtures, then this number blows up. You want to design new MOFs, you need ligands, this number blows up. You want to design dipeptidic solvents, binary ternary mixtures, this number blows up. You want to design ionic liquids, well, any one of these molecules can become a cation or an anion. And again, this number blows up. So we should be able to navigate that space with machine learning, with GPs. But we do have one issue, which is molecules, molecular structures, they're not numbers. And machine learning models, the input, they need numbers as inputs. They're mathematical models. And so the question becomes, if we want the input to be a molecule and the output to be a property of that molecule, then we need to find a way to convert molecular structure into a set of numbers, which is known as trying to featureize a molecule. And there have been many proposals in the past of how to do this. Things like fingerprints, things like smiles, potentials, graphs, sometimes matrices, Coulomb matrices, and even the coordinates, the 3D coordinates of the atoms of a molecule. But there's a lot of issues with these approaches. First of all, there really is not a lot of chemical information in many of these representations. In smile strings, for instance, you're treating carbons as Cs. The machine learning model has to learn that a carbon is an atom with a given area, with a given polarity that has the potential to interact with other molecules in different ways. It has to learn that a hydrogen bonded to an oxygen behaves very differently than a hydrogen bonded to a carbon, for instance. They're not human intelligible, many of them, and the most important thing, they have no standard input size. So you see, for instance, the smile string of water is very small, smile string of decane is very large. Same goes for Coulomb matrices, same goes for graphs, same goes for fingerprints, electronic density for coordinates. Basically, the input of your model, and you do have to pre-select the architecture if you're using a neural network, although this is not as much of a concern in GPs. The input of your model, you have to make it as big as the largest molecule in your data set. So if your data set has a C20, an alkane with 20 carbons, then your input is going to be huge. And this means a lot of parameters to optimize, and this means a lot of data inefficiency. And you need tens of thousands or hundreds of thousands of data points to get the model to fit. Well, Sigma profiles offer quite the elegant solution to this conundrum. And what are sigma profiles? Well, let's say you take a molecule like ethylene glycol, you go into the FT, you build the van der Waals surface of this molecule, and then you tessellate that surface into small triangles. You then compute with the FT the screen charges on top of each one of those triangles. This basically is an electrostatic potential map, but with some nuances, in particular because these calculations are done in what's known as the Cosmo-Continuum solvation environment. You then take this surface and you build a non-normalized histogram, where the y-axis is the amount of surface area or number of triangles that has a specific screen charge. And all of a sudden, you have a plot composed sometimes of 51 points, sometimes of 61, depends on the range and the binning that you decide that you pick for this histogram. But it's usually with steps of 0.001, and so it yields either 51 or 61 or 71 points. Now you have a vector of numbers with a fixed size that tells you a lot about the polarity of a molecule, and therefore tells you a lot about its potential to interact with other molecules, which we know is crucial to describe physicochemical properties. Now, we decided to try to train both neural networks and GPs with Sigma profiles. And the idea is always the same. We don't want to use hundreds of thousands of data points. We want to use compact models so we can actually get useful models with very few data points. We went into the literature. We got ourselves a very diverse Sigma profile database containing about 1,400 compounds. A lot of organic families, alkanes, alkenes, alkynes, alcohols, aromatics, halogenated compounds, acids, bases, also some inorganic compounds, some inorganic solvents, gases, water. And we took those Sigma profiles and we took the boiling temperature of most of those compounds, about 1,000. And we trained a neural network where the input were the Sigma profiles of the molecules, the output is boiling temperature, and we also trained a GP. And we actually had already done these neural networks in a paper from 2022. At that time, we had no idea that GPs would be more efficient than neural networks. But cholera surprised. Neural networks, to predict boiling temperature, they gave us R-squares for the training set, here represented in red, of 0.96, testing 0.90. GPs far outperform neural networks. And what's more interesting is to train a neural network to do all of the hyperparameter tuning, it took us about a week in HPC clusters, so specialized computational resources, a week. GPs took us 10 seconds to train them on this laptop here that I'm using today to talk to you. So it's a huge computational efficiency boost when we disregard neural networks and start using GPs. We decided to then fit GPs for a lot of other properties. So what you are going to see are always predicted property versus experimental property. Red is a training set. So molecules that we use to train the model. Blue is the testing set, so molecules that the model has never seen before. And we get very good predictions for molar mass. But no one really cares about molar mass. So boiling temperature, like I just showed you in the previous slide, very good predictions. Our training of R-squares of 0.98, testing R-squares of 0.95. And look at the range that we are predicting. We are going from -200 Celsius, so really liquefied gases, all the way to 500 Celsius, heavy oils. So from now on, if you want to predict the boiling temperature of a molecule, You get the sigma profile of that molecule, you feed that sigma profile into this GP, and in a millisecond, it tells you its boiling temperature. Of course, I'm not saying that this is perfect. This is not perfect. The absolute errors are about 10 degrees for the training set, 16 degrees for the testing set. But in a screening scenario where you want to screen the boiling temperature of 2 billion molecules, this type of error is, well, it's not that large. You can screen those 2 billion molecules, 5 billion molecules, 10 billion molecules, and then pick the best 10, the best 15, the best 20 given to you by the GP, and then actually more carefully examine those molecules with, say, molecular dynamics, with, say, experiments, anything you want. So this really is a tool that allows you to navigate the space, the chemical space, very efficiently so that it doesn't take you 300,000 years to actually pick a molecule for whatever application that you need. Here we have vapor pressure, same story. Again, look at the range of vapor pressures that we're predicting. We're covering pretty much a 7 or 8 orders of magnitude. We also have density. Density is an interesting one for me because we found quite the outlier here. This is a weird phosphorus-sulfur cage compound. Other than that, very good predictions for density. And I must add that in this case, we make no distinctions between solids and liquids. We just want the density at 20 Celsius, which means that the model also has to learn whether a molecule will be a solid or a liquid at 20 Celsius. Refractive index, same story. And to me, what is the most remarkable result of this work? Solubility in water. Why? Because of the training size. We were able to obtain this level of accuracy with just 300 data points. So with 300 different molecules, with solubilities ranging from 10 to the power of -5, so pretty much something that's absolutely insoluble, to solubilities in the order of 10 to the power of 4, so things that are almost miscible with water. So we're pretty much covering 10, 11, 12 orders of magnitude. 300 molecules are enough for us to now be able to predict the solubility, the aqueous solubility of any molecule out there within, of course, testing R-square of 0.88. So perfect for fast, quick screenings. Now, again, just like we saw before, we can train GPs to predict properties. Okay, before we were doing this by inputting composition temperature. Here we're doing this by inputting sigma profiles. But can we actually use GPs as laboratory companions? In other words, what if I have a property, I'm interested in a specific property, but I have no data for it whatsoever? Can GPs still help me? Yes, they can. And to show you this, first, I'm just going to tell you that sigma profiles here, they have 51 dimensions, or basically each sigma profile has 51 points. But I want to be able to represent sigma profiles in a 2D space so we can actually see GPs progressing and exploring different molecules. And to do that, I did PCA, principal component analysis, just for visualization purposes. This is not the input to the models, just for us to see sigma profiles as a space. And so basically you get this nice 2D space where each point, each circle represents a different sigma profile, or in other words, a different molecule. And now the question is, okay, let's say that I want to find, out of a universe of, say, 1,000 molecules, I want to find the molecule with the largest boiling point, just as a random example. But I have no data, zero data. I don't know the boiling temperature for any of those compounds. I pick one molecule at random, I go into the lab and I measure the boiling point for that molecule. I train a GP model on that single point where the input is the sigma profile of that molecule, output is a boiling point that I just measured, and then I compute acquisition function, which is basically the uncertainty of the model. Here, this is in a Bayesian optimization scheme, so we're telling the model, we want you to be able to predict boiling temperatures, but our goal is to find the molecule with the largest boiling temperature. So the model has to weight both things at the same time, increasing its accuracy and increasing the likeliness that it has found the global maximum. The model weighs both things using this acquisition function here, known as expected improvement, and tells us, well, my expected improvement is largest for this specific molecule. We go back to the lab, measure the boiling point for that molecule, and we keep doing this iteratively. So what does this look like? Again, we have about 1,000 molecules. We want to find the molecule with the largest boiling point. We start with carbon monoxide. Why carbon monoxide? Because it's the worst possible guess, and we wanted to challenge us. We start with carbon monoxide. We train a GP model on this single data point. Again, there is no other types of data. It is literally a machine learning model trained on a single data point, input sigma profile, output boiling temperature. And the model starts asking for things. Finds out about halogenated compounds, starts asking about halogenated compounds, finds out about rings, aromatic, finds out about carbons, finds out that if you put a lot of carbons, you get the largest boiling temperature, finds out about oxygens, these functional groups, these ester functional groups, and all of a sudden, it has found the molecule with the largest boiling temperature. In fact, in just 15 iterations, it found the global maximum of our database. So in the universe of 1,000 molecules, you don't need to go to the lab and measure the properties of each single one of them. No, not even half, not even a third. No, 15 iterations was enough to find the perfect molecule for our application. And I'm giving you boiling temperature as an example. Oops. But we did this, and you can check the details and the results in this paper that we published last year. We did this for a lot of other properties. We did this for density. We did this for refractive indexes. We did this for vapor pressure. We did this for aqueous solubility. We did this for, I think I've covered most of it. We did this for molar mass, although I'm sure none of you care about molar mass. And the results were always the same. We can find global maximum in 10, 15, 20 iterations. And what this means is you want to dissolve a target compound. You go, you have your lab, you have your colleagues' labs, and between all of you, you have like 1,000 solvents that you could try. You don't need to try them all. You can use something like this to guide you into which solvents to actually try to minimize the amount of data, the amount of resources, the amount of trips that you have to make into the lab to find your perfect solvent. You want to synthesize the perfect MOF? Same thing. You want to design the perfect ionic liquid by combining a specific cation and an ion? Same thing. You want to get into mixtures? You can also get into mixtures. In fact, we were so baffled by the ability of GPs to basically navigate databases of pure compounds. And of course, our database had about 1,000 compounds, but it can have any number. And it can be what you have in your lab, like I said, or it can be maybe what you can buy from Sigma or from any other supplier, maybe what you have in PubChem, or maybe you're actually interested in all of those billions of molecules that are out there. And so that can be your space as well. You pick your space. Well, coming back now to this idea of mixtures, we said, well, this works well for pure compounds, for molecules. What about mixtures? Can we do something there? Yes, we can. And we started with a hydrotropy because this is really something that we find very amusing. You see, you have a hydrophobic solute, very low solubility in water. You add an amphiphilic molecule known as the hydrotrope, and depending on the chemical and structural nature of that hydrotrope, depending on its size, on its apolar volume, it will aggregate around the solute and boost its solubility in water. And you can enhance the solubility of your hydrophobic solute 10 times, 100 times, 1,000 times, 10,000 times, depending on the hydrotrope that you choose. What's also interesting is it also works from the other way. So if you have some sort of liquid solvent and you dissolve a hydrophobic solute in that solvent, paradoxically, if you add water, small amounts of water into that liquid solvent, you actually boost the solubility of the hydrophobic solute. This is known as hydrotropy, and you can read all about it. We have a lot of works investigating this mechanism, but we wanted to see if we could try GP's machine learning as well. So we went into the literature and basically curated a database of solubility enhancement for syringic acid. So the solute that I showed you a few minutes ago, but from the perspective of describing solubility as a function of composition and temperature, here we're going to look at this from the perspective of predicting solubility of this syringic acid in mixtures of water and hydrotropes, but the input now is the sigma profile of the hydrotrope and the composition. And for this data set, and I will tell you that the data set is limited. There's not a lot of points that we could find in the literature, only about 100 for the training set, about 50 for validation, about 40 for testing. But even with this very limited database, it would be completely unthinkable to even start training a neural network and many other types of machine learning models on such a small data set. But with GPs, we have no such issues. We get the sigma profiles of the hydrotropes, and we were able to train the model. And here what you have is the predicted solubility enhancement of syringic acid versus the experimental one. Training R-squares of 1, so perfect predictions, validation 0.99, and testing, so molecules that were never seen before by the model, 94. And that allowed us to go to the lab and, well, find new hydrotropes to boost the solubility of syringic acid. It is that easy, and it is something that you truly should consider whenever you're trying to find mixtures of solvents for a target solute or for a target application. Again, confidence is the key here in GPs because they predict uncertainties and they can tell you which ones which ones you should try. Now, diepithetic solvents, we were also very interested about this because they're mixtures. And this did work for hydrotropy, but the data set was quite limited and it was for a single solute. What about DESs? Basically, you can mix literally anything that doesn't chemically react. You can mix and you get a eutectic, or usually you get a eutectic type phase diagram. If you mix solids, sometimes you get liquids. Predicting the properties of such a big, large amount of binary mixtures is unfeasible. And it's funny because in the literature, despite the fact that we found large data sets for density, for viscosity, for melting temperature, there were not a lot of unique precursors as I'm about to show you. But what we did here was we want to be able to have GP models capable of giving us the density, viscosity, and melting temperature of any DES that I can think of. We went into the literature, got ourselves data sets, density data set, the viscosity data set, melting temperature data set. A lot of points here. We did find about 3,000 for viscosity and density, about 1,400 for melting temperature. Here's the validation and testing sets. We calculated the sigma profiles for these DESs, and here are the predictions. Again, predicted versus experimental property, excellent predictions for density, excellent predictions for viscosity, excellent predictions for melting temperature. And look at the range that we're covering. Again, we're going from things that pretty much don't crystallize at all and just showcase glass transitions to things that pretty much start decomposing by the time that they start melting as well. And even then, our average error for the testing set is just 10 Kelvin, which means that we can now start designing DESs for any application that we care about. What we found, though, was despite the size of the data set that I just showed you and our ability to predict the properties of those DESs, there were only 750 unique DES precursors. So despite we having 5,000 or 6,000 different mixtures, they were always composed of choline chloride, sometimes betaine, a lot of water in there as well. So the common precursors, basically only 750 different molecules in that huge data set. So the first thing we did, well, let's augment this. Let's predict 60,000 new DESs from unique precursors that no one has ever used before. And from this, we started then picking these peaks here and these peaks there, trying to maximize viscosity and density or minimize viscosity and density. Same thing for the melting temperature to design a bunch of different solvents for different applications, including lubricants. This is a really nice work, gave us a lot of excitement to do, and it will be published soon. So if you want to, I can send you an early version as soon as we get it out. Do send me an email if you're interested. Now, this idea of using sigma profiles as inputs in machine learning models, be it neural networks, be it Gaussian processes, be it random forests or any SVMs or any other type of model, it didn't come to us in a vacuum. It came to us because we were already using Cosmo RS, which is a thermodynamic model that uses sigma profiles to predict activity coefficients. It's a thermodynamic model. It has nothing to do with machine learning, but it's a very powerful predictive tool to get activity coefficients and phase diagrams. And we have a lot of experience using Cosmo RS. Over the years, we've been using this to predict activity coefficients, to then predict phase diagrams for DESs. We've done this also for choline chloride-based DESs, which has this issue of choline chloride being a salt. We've also done this for vapor-liquid equilibrium of deputatic solvents with great accuracy. Solubilities, of course, solubilities of things in DESs or solubilities of things in other solvents. Cosmo RS works very well to predict activity coefficients. Again, nothing to do with machine learning. It is its own model that it's also part of our collection of tools that we use daily to design novel materials. But it does come with its issues, and mainly there are two issues. First is Cosmo RS is expensive. It's paid software, it's not open source. Second one, and this is an issue common to both Cosmo RS and all of the machine learning approaches that I showed you. It takes time to get sigma profiles. It takes between minutes to hours to get a single sigma profile for a single compound. And with this in mind, we partnered up with Simon Mueller and Irina Smirnova to come up with a solution. They've published an open source Cosmo RS implementation. It's already available. You can use it. And they're getting their sigma profiles, which are actually in their case sigma matrices, from Orca, which is free software for academics. And they had this very nice large database containing about 13,000 different sigma profiles, both for neutral molecules and ions. And we said, well, we've already published before a model capable of predicting sigma profiles. But you have this very large database with sigma profiles coming from free software. Let's try to get a machine learning model that can actually predict those sigma profiles, which in this case are actually sigma matrices. Here we use a graph convolutional approach. Basically, we take a molecule, we take its atoms, individual atoms, and we compute their chemical environment depending on their neighboring atoms. We describe the atoms with MMFF atom types, which is something that we've shown that works very well in graph neural networks. And we use basically a convolutional type of architecture, very similar to another one that we've published before to predict sigma profiles based on the Mullins database, a much smaller database with about 1,400 compounds. And well, here you have it. We are able to predict both the volume of the molecules of all of these species, but also the sigma profiles with very, very large accuracy, both for the training, validation, and testing set. And just as a few examples, here's thymol, here's the predicted sigma matrix from our machine learning model, from our graph convolutional network. And this yields two different sigma profiles. It's based on the open Cosmo RS theory and approach to sigma profiles. Again, they're matrices, not profiles. What's the difference between these two profiles? The averaging radius that you use when you do the averaging algorithm. So basically the radius that you use to probe the molecule. Choline chloride, again, here's the sigma matrix and here's the sigma profiles. This is what our model predicts. We then sum columns or sum rows to get these two, and you can compare against their quantum chemistry counterparts. Red are the GP predictions, black are the quantum chemistry counterparts. Very good predictions. And what this means is, well, we can now predict the sigma profiles of any molecule that you can think of in a millisecond. And so if you want to go and navigate 200 billion molecules, you can, because you can start by predicting their sigma profiles, and then you can take those sigma profiles and feed them into our GP models and predict whatever properties you want. Or if we don't have GP models for the property of interest, you can then do those Bayesian optimization approaches that I showed you, where the GP model navigates you and tells you what you should be measuring. We also took these predicted sigma profiles and reparameterized OpenCosmos-RS. And you can see, of course, it's not perfect. Here you can see the partition coefficients predicted by the original version of OpenCosmos-RS, and here predicted using our sigma profiles, our predicted sigma profiles. So there is a small decrease in performance. In terms of our activity coefficients, the decrease is not that significant. We go from 98 to 97, although actually these results are already outdated. We improved our model slightly. And nevertheless, you can now, without any sort of specialized knowledge in quantum chemistry or thermodynamics, give us a molecule, or give to this model a SMILE string, or draw your molecules, predict the sigma profiles, and feed those sigma profiles directly into OpenCosmos-RS to predict activity coefficients. This bundle of software combining OpenCosmos-RS and sigma profile predictive capabilities is a work in progress. It's nearly finished and will be available soon. So again, if you want to be kept in the loop, please send me an email, and I'm more than happy to do so. I would also like to highlight this ongoing work. We already have a preprint here, and this is a kind of a software wrapper that we've developed to compute sigma profiles using open source software. And this was an issue of ours. We were always very troubled by the fact that we couldn't compute sigma profiles using free and open source software. It was always either paid software or free software that was not open source, or free software that didn't allow us to divulge the sigma profiles that we computed, or free software that we had to patch to get sigma profiles. So we were quite unhappy with that and developed this wrapper for NWChem, where basically you can put an identifier and compute a sigma profile. This is not the same thing that I just showed you. One is a machine learning approach that we like for OpenCosmos-RS, gives you sigma profiles that you can also use for GPs and anything else. Here you can actually get sigma profiles by changing conformers, by doing weird structures. So it gives you a lot more flexibility for any need that you may have to then use those sigma profiles in Cosmos-RS or machine learning models. And with that, well, I know this has been a quite heavy presentation. I've shown you a lot of things, and I don't want you to feel overwhelmed. What I want you to understand is these machine learning tools are here. They are very, very useful. You don't need to have the expertise to use them. You don't even need to know Python to start using these tools. You can use them to predict properties for a given system as a function of composition and temperature, for instance, or pressure. You can use them as a laboratory companion, where you want to drastically minimize the amount of data that you need to get your properties. Or you can use them to predict the properties of different molecules, or you can use them to tell you which molecules you should be measuring in the lab to find the best one for your application. And with that, I'd like to thank the research groups that I've been involved with while developing all of this research. A lot of it was from my time as a PhD student under Professor Yamil Colon and Ed McGinn, and also now with Professor João Coutinho here at Aveiro, also from my undergrad in Aveiro. And with that, well, thank you very much for your attention.